This video is a quick run through of the 2018 paper 2 question 8b part 1 question. So we have got a grid with 4 statements and we have to say if they're always, sometimes or never true. The first statement is saying that when we're forming confidence intervals for fixed n and p hat, so if n and p hat don't change, then an increased confidence level implies a wider interval. To better understand this statement, let's go and have a look quickly at a sketch of a normal distribution. So imagine that I've been doing a question involving sample proportion and population proportion, and I've found my sample proportion p hat, and I'm trying to figure out then a confidence interval for where the actual population proportion lies in relation to that. If my confidence interval takes me to plus and minus 1 standard deviations either side of that sample proportion, then I've got 68% confidence that I'm capturing the population proportion within that range. Now, I'm going to just use the empirical rule as I do this just for ease of communication. But you know, obviously 1.96 is important when it comes to our standard error. So I've gone out plus and minus 1 standard deviations. Now, if I went out further than that, again, sticking with empirical rule, imagine that I went out plus and minus 2 standard deviations either side of that value. I'd have a 95% confidence interval that I've captured the population proportion within that range. And of course, I could go further out again to plus and minus 3 standard deviations, in which case I'm capturing 99.7% of my data, or I'm kind of expecting that 99.7% of the time the population proportion is going to be in that margin. So I've got 99.7% confidence that my true population proportion is in that particular interval. So essentially, the further out I go from my mean, the more certain I am that the real population proportion is in the interval that I have. So a wider interval gives us an increased confidence level, and that relates to what they're saying in the question, which is that an increased confidence level implies a wider interval. So that's true, always. Taking one last look there at that normal distribution, it's interesting to note that as my confidence increases and the range of values increases, the accuracy with which I'm able to pinpoint the possible range of values in which the population proportion might fall actually gets less and less accurate. Okay, so on to statement 2. As the value of p hat increases for fixed n, so n isn't allowed to change, p hat is the only thing that can change, the estimated standard error of the population proportion increases. So let's have a look at our standard error formula. So that was sigma p hat equals to the square root of p times 1 minus p over n. Now, you might remember that when we talked about this in class, we said that if p, the population proportion, isn't available to you, that you can work with p hat, the sample proportion, instead. Because, of course, that's the best estimate you can get for p, and that's what they're asking us to do in the question. They're saying that p hat is going to increase. Note that since p hat is the proportion of the sample that are in agreement with a particular statement, that p hat can be between 0 and 1, but it can't go outside those boundaries. The lowest p hat can be as 0 and the highest it can be as 1. So what we're looking at there is, as we fill in increasing values of p hat, what's going to happen to the value of our standard error? And if you're unsure of this, the best thing to do is actually test it and see what happens. So I'm going to take a value for p hat and sub it in and see what happens to my standard error. And then I'm going to take a few more values where p hat gets larger and see what the result is. I'm going to start off with p hat being 0.1. So when I fill that into my standard error formula, I've got the root of 0.1 times 1 minus 0.1 over n. Now, we're going to only be able to evaluate the top part of this fraction. We're going to get root 0.09 over n. I could do a little bit of more tidying up there to get 0.3 over root n for that. So if p hat is 0.1, then the standard error is 0.3 over root n. So let's go up now a little bit with p hat and see what the result is. This time I'm going to test p hat being 0.3. I'll do the exact same thing as before. I'll sub it into that formula and see what happens. So I've subbed it in and I've simplified slightly there, and now I'm going to evaluate root 0.21. So in the case where p hat is 0.3, I'm getting 0.458 over root n. So far it looks to me like, okay, well, the standard error value is after increasing, but is that going to continue to happen? Take a moment yourself now to do the same calculation for standard error using 0.5 and 0.7. Write down your result and then try to make a decision about whether the statement was always, sometimes, or never true. So when we have p hat being 0.5, then the standard error is 0.5 over root n. At this stage, it still looks like it's increasing. But when we evaluate it for p hat equals 0.7, we get 0.458 over root n. Actually, that's the same value as we had for 0.3, isn't it? So it reaches a maximum value and then begins to decline again. So in some situations, when we increase our p hat value, the result for the standard error is going to go up. But in some cases, when we increase our p hat value, the result is actually going to go down. So this particular statement is only sometimes true. So when p hat increases, sometimes the standard error goes up, but not always. You can take a similar approach for statements 3 and 4 by actually taking values and subbing them in and trying to figure your answer out that way, but we can do it a little bit more abstractly too if we like. Statement 3 looks really like statement 2, so it's important to just read it carefully to note the difference between them. In 3 it says, as the value of p hat times 1 minus p hat increases, and n isn't changing, so n is fixed, the estimated standard error of the population proportion increases. So again, let's have a look for a moment at our standard error formula. They're asking us to focus in on the numerator of this. And they're saying to us, as this particular expression gets bigger, is the overall value going to keep getting bigger? So I'm going to have a think about this and say, well, okay, p hat times 1 minus p hat is increasing. So as that increases, what happens to the square root of it? Is that going to keep increasing as well? Well, if you keep taking bigger and bigger values and finding their square roots, the square roots will keep getting bigger and bigger as well. So as p hat times 1 minus p hat increases, the square root of that value also increases. And of course, the square root of p hat times 1 minus p hat is the numerator of our standard error formula. And as a fraction's numerator increases, the value of that fraction increases. So as p hat times 1 minus p hat gets bigger, the root of p hat times 1 minus p hat gets bigger, and the fraction overall gets bigger. So the standard error gets bigger. So that means that our statement is always true. Finally, we've got statement 4. So as n, the number of people sampled, increases for fixed p hat, so p hat's not going to change, the estimated standard error of the population proportion increases. Right, so again, we're back to this formula again, except this time we're having a look at the n. So the top value, whatever it is static, and it's just the n that's changing. So now what's happening as that n value gets bigger? So as n increases, the square root of n increases. So as the n here gets bigger, the square root of n gets bigger, that whole denominator is getting bigger and bigger. And what happens to a fraction as its denominator gets bigger and bigger? Well, as our denominator gets bigger, the overall value of the fraction gets smaller. So now what were they saying to us in the statement? They were saying as n gets bigger, the overall value gets bigger as well. Well, that can't be true, because we just established that as n gets bigger, the overall value of the fraction is going to end up getting smaller. So that particular statement is never true. It might be worth watching back over this a couple of times to really get clear in your head exactly what's going on. And again, with questions like this, where it's possible to put values in, I'm thinking of statement 2 here particularly, where it's possible to put values in to test the statement, that can be a really good idea so that you can get a really kind of clear handle on exactly what's happening, and then you can be very confident in the choice that you make for your answer.